The meeting is now in session.
Good afternoon, wherever you may be. My name is Emily, and I will be the host for today's presentation. I would first like to take this opportunity to welcome you to this exciting presentation, Astonishing Enhancements to Signal Integrity EDA Tools using 3D Vision and GPUs. Today we discuss, in a close and wide-ranging collaboration, Agilent and NVIDIA engineers have combined signal integrity EDA tools with 3D vision glasses and panels to produce insights needed for the next generation of NVIDIA chips. In the past, you know how you can benefit from the virtuous circle of better hardware helping EDA tools run better, and better EDA tools helping design even better hardware. We'll show NVIDIA benefits from massively parallel EM and circuit simulation by running its design system on PCs with NVIDIA Tesla or Quadro professional GPUs, and how 3D visualization of EM fields gives better insight, literally, into EMC/EMI issues. For this presentation are Dr. Fahmy and Amalek Badesha. Dr. Fahmy is a director at NVIDIA, dealing with the design and analysis of high-speed digital and analog interconnecting systems. Before NVIDIA, Dr. Fahmy worked at Intel, Micron, and TI. He has a PhD from the University of Toronto and a Master of Science and Bachelor of Science from Cairo University in Egypt. He is an application expert with Agilent EDA, which focus on signal integrity and EMI. He plays a critical role in driving Agilent's signal integrity initiative by creating innovative products and strong customer engagement. His background RF and microwave design with prior experience in handset applications. He has a BS and MS degrees in electrical engineering. A couple of important items before we begin today's presentation. Please feel free to ask questions at any point throughout this presentation. You can chat directly to our question manager, Colin Warwick, who will forward questions to the presenters. We will address all questions at the end of the presentation. If we're unable to answer all of your questions, one of the presenters will follow up after the presentation via email. I'll take a moment to fill out the short feedback form at the end of the presentation. You'll be automatically entered into a draw to win a U1242A handheld digital multimeter. I'll turn the floor over to Amalek to begin.
Thank you, and welcome everybody. And today's talk, we'll be talking about astonishing enhancements to signal integrity and EMI tools for using GPU and stereo vision. Here's the line of today's presentation. We'll briefly talk about the partnership between Agilent and NVIDIA and how that has resulted in some really exciting tools to solve challenging signal integrity and EMI problems, and really have designers and users of these tools inside the company to do better hardware design. So we'll talk about that and what has come out of that partnership, and then jump into real examples of how these tools can be used signal integrity and EMI applications. So the first part will focus on signal integrity applications, and I'll show you a specific example of memory channel optimization. In part of the presentation, we'll talk about state-of-the-art EMI design workflow, and with a specific example of dampening memory simultaneous switching output radiation, and also introduce a very exciting new technology called 3D stereo visualization of Maxwell fields. And we'll talk about that and then conclude and Q&A after that. The benefits of the partnership that we have between Agilent and NVIDIA, it is making faster and faster processors that can be used to speed up simulations. So we take that hardware and use that to speed up our simulations, and in turn helps NVIDIA designs even faster hardware that we can use for even faster simulations. So a very nice virtuous cycle that helps both companies do better design and faster, more efficient simulations. Gives you a full overview of what we have been able to accomplish just within the last year and a half of our collaboration. The NVIDIA design teams had a need to reduce cost of their PCB packages cloud simulations. So to them do that better, Advent introduced 3D stereovision for Momentum and EM Pro tools. In addition to a post-layout model for the channel, NVIDIA needs accurate transistor-level modeling, but tool modeling takes very long. So to address that, Agilent introduced GPU-accelerated transient simulations. Now, to complete the picture, to do full system-level simulations, you need to include 3D structures like connectors, cables, dowels, and so forth. Again, to help that problem and to do it in efficient and time-efficient manner, Agilent introduced the GPU-accelerated EMO FDT solver. And combining these different tools, we have developed a methodology to robust EMI design, which we refer to as Virtual EMI Lab. And we'll discuss this in more detail in the second part of the presentation. So now I'll pass the speaker on to Hank Fahmy, who's the Director of EMC SI Engineering at NVIDIA, and he's an active user and developer of this methodology.
So introducing myself, thanks really for introducing me, Amolak. So we're starting here by showing a challenging example of how to optimize the memory channel on our GPU cards using this innovative approach. Maintain in our minds that we'd like to improve the performance of memory channel, maximizing as much as we can, because if you guys know that on the GPU cards, maximizing the memory throughput is one of the key parameters to gain performance. And time, as everybody knows, that we'd like to get the minimum cost of our boards and our systems. Now, the next page. On the top, we have the traditional workflow that most of the signal integrity engineering teams are doing today, which is spending most of the time in the pre-layout simulations to develop design guidelines. These guidelines are adopted by the layout designers, trying to implement it on the real board while having a lot of constraints about the cost, about the layer count, and so forth. They meet a lot of challenges during the layout of the board. In that, they take these challenges without any data-driven simulations and go ahead with it, with the revs of the board depending on the electrical validation to try to test whether we met the PR performance requirements or not. The traditional workflow, it's high cost, it's iterative, it's data-driven, and loss of sleep for signal integrity engineers. Then go on the bottom, which is really helping the layout designers do such trade-offs with data-driven post-layout simulations. So while doing the layout, the signal integrity engineer would actually support the layout designer with simulations of the actual post-layout. Try to optimize the layout momentarily in a reasonable amount of time. And instead, depending on the iterative approach for the electric validation, depend on data-driven accurate simulations. Now, the problem with the bottom approach, it's indeed going to be helpful and provide happy life for signal integrity engineers, and only if it can provide data within reasonable amount of time, and also if they are meaningful data. Actually moves us to the next page, how we get meaningful data. I know the regular term garbage in, garbage out is well known in the computer industry. We mainly are hoping to get accurate modeling of the passive interconnecting systems, mainly on the PCBs as well as on the packages. And there was actually a very nice discussion in the SI list. Up to the bottom line is correlation. Yes, signal integrity engineers, correlation is a critical parameter for us. Actually, what we have done is that we took one of our boards, and there are no resources available to do the VNA measurements, then all the time we can actually get it and outsource it to external test labs, such as here, we got the courtesy of the GEICA test labs here in the Bay Area to do the VNA measurements for us on one of our GPU cards. The VNA are measuring the insertion loss and the return loss of the channel for us, from the GPU side to the memory side. And again, the bottom line is correlation. We want them here to correlate to the VNA measurements. And we get very good correlation of the insertion loss and the return loss. And actually an important point here, that most of the full wave techniques, they actually provide accurate modeling that correlate with VNA measurements. These techniques are momentum, are finite difference time domain, are finite element, tools as momentum, as HFSS, as CST Microwave Studio, they would all correlate with the VNA measurements. The bottom line for us was actually to get these correlations and these accurate data in a reasonable amount of time. And V team's investigations, and thanks really to my own internal teams here in Shenzhen as well as in the US, headed by Chuck Jackson and Charlie Chu, we found out after correlating different tools, we found out that the full wave techniques do indeed correlate. The first of them was momentum. That's the reason we have chosen momentum for this post-layout simulations. You see on the bottom, well, a picture here, we have a complicated memory module that's from the GPU to the memory devices. And you can, from here, we can actually extract the post-layout for all these address signals, get an accurate S parameters of them. Accurate fast interconnecting modeling is a key parameter. But that's enough. We move next page, and this is a very realistic example that most of us face today. The boss tomorrow is asking me, shall I go with the 10-layer board routing or the 12-layer board routing? On layer board routing, we are here routing the memory channel. It's a whole plane from the GPU card or from the GPU chip to the device. And it's a 10-layer card, and it mainly have limited area, real estate to route the memory channel. You have to sacrifice the impedance and run and route thinner traces at 50 ohms. And we have to relax the spacing. We have to go a smaller spacing between the traces. Option is a 12-layer card where we gain 2 more layers. And because of that gain, we kept actually the traces thicker at 40 ohms impedance. And we also adopt strict spacing requirements, which is a wider spacing. And you clearly see here in this picture that the state taken to route this byte lane on GPU card 2 is larger than the real estate taken to route the same byte lane on 10-layer card. Now, from a marketing perspective, they would prefer the 10-layer card only if we were able to meet the electric performance requirements for that memory module. Now, the question is, can we, the 10-layer card, meet our POR requirements or not? The answer is we do need accurate modeling of the memory channel. Now, this is extracting the whole byte lane, 11 nets with 22 ports, on 10-layer board with a whole byte lane taking 1.5 hours on an 8-core machine. On the 12 board, it takes approximately 2.5 hours, which is, these are reasonable amount of time that we can extract the S parameter modeling up to 20 gigahertz for these 2 boards. And we need another maybe 5 hours to extract the package. Therefore, we can have an accurate modeling of the GPU package and board as well as the memory device. Now, the S parameters alone are not enough to judge the performance delta. It's that we have accurate modeling of the passive interconnects, but everybody knows that we need also an accurate modeling of the linearity of the drivers and the receivers. The key is actually the transistor modeling. However, let's go to the next page here and see that within 3 minutes, we can linear driver simulations with a pseudo-random bit sequence, mainly harshly stress the memory channel. You get 1 gigabit per second within 3 minutes. We find the performance delta between the two cards is negligible. The POR is 1 gigabit per second for these two cards. Then definitely we can get data-driven answer to the layer designer that go ahead with the layer card. The next page, what about 2 gigabit per second if the POR is 2 gigabit per second? Again, linear driver modeling, within 3 minutes, we can get these eye diagrams of all the bits. The problem is neither eyes can meet the performance requirements and DRAM setup and hold timing requirements. The question is, are these simulations accurate to provide this data at 2 gigabit per second and say that both cards fail at 2 gigabit per second? The answer is no. We have all the time to understand how the memory channel protocol is working, whether the PRBS at this data rate is a good matching or good emulation of the memory protocol and the signaling on this memory channel. The answer is no. Therefore, we must go to transistor level model simulations. Most of these, they run away from transistor model simulations because it takes very long time to run, and agree with them. But with the help of the top-notch software and hardware technology, we're able actually to get the CPU and GPU working together in a heterogeneous environment, where we can actually get a fascinating speed up of the transistor simulations without any approximations to the transistor model simulations. So instead of 3 minutes with the lead driver model, it's up to 3 hours. This 3 hours, actually, it's much better shape than 15 hours taken to run transistor model simulations. So within hours, we still can get full channel modeling. And at 2 gigabit per second, we can get that the performance of GPU card L1 is 45% of UI, and the GPU card 2 is 47% of UI. This 10-layer card is only 2% off performance than GPU card 2, but the answer is still we need the performance of 2 gigabit per second with the 10-layer card, because this 45% is to give the memory channel the required setup and hold timing requirements, along with all the other errors of sending the strobe inside the data eye. The key here is accurate modeling of the drivers and receivers, as well as accurate modeling of the passive interconnecting system. Now, we were able to do that, as I mentioned, especially with transistor model, when you get acceleration from our Tesla products and our Cadro products as well. This is Tesla C1060 card, and this is Tesla that have 4 GPU cards in it. If you bottom graph, this one GDDR5 simulation takes approximately 15 hours per simulation corner. You get down, once you incorporate the GPU, down to 3 hours or 5 hours at most. Actually, 30-hour circuit 2 actually runs over a day in 30 hours. With the help of the GPU, you can drop it down to 5 hours. The speed of 6x at least is actually very appreciable, and indeed does depend on the complexity of the transistor model simulations. You can get much better speed up than 6x up to maybe 20x or 30x with less complicated circuitry. And I can refer to Agilent, actually, folks, to get more details about the speed up of the transistor simulations without losing the accuracy of the transistor model. Idea here is that how you can get this heterogeneous environment between the CPU and the GPU and the accuracy of the transient simulations from the tool working hand in hand to get accurate modeling of your channel. The answer to that card performance doesn't stop at whether we met the performance or not. All signal integrity engineers are smart and thinking outside the box, and would say that it's not enough just to meet the performance. By the time my manager used to challenge me, where we are at the performance cliff, Are we close to the cliff, or are we at the cliff? So as data rates goes high, we know that the performance gets down. But the question is, what our design performance? Are we on the flat portion here that is a happy face, or are we crying on that falling edge of the performance? That's why next page, we're actually going even higher at 2.5 gigabit per second. Again, these data rates, we need accurate modeling, therefore use the transistor model simulations, and get actually a fail eye masks of both cards that both fail at 2.5 gigabit per second. Are we going to stop at this point, or again, we're trying to think outside the box? As signal integrity engineers, we're trying all the time to optimize the channel, but we optimize each parameter independently, optimize the impedance and crosstalk independently from the return path discontinuity, from the driver linearity and driver characteristics and receiver characteristics. The answer at these data rates, we must optimize the channel concurrently. We optimize the impedance, the return discontinuity in terms of whether the signal that changes layers or not, the required stitch vias, the proximity of the stitching vias to the signal layer transitions. This is a GPU side. You can see here the black lane is routed on the 10-layer card, and because of the thinner routing of the traces of 50 ohms, it gives us actually real state that we can place a number of stitching vias that help in the signal layer transition. And we'll be able to see such type of impact as we do accurate S-parameter modeling of the passive interconnecting system that acts in energy and try to see whether the energy goes to the other side of the channel or not, how is reflected, how much is transmitted, how much actually is mainly is blocked by the impedance discontinuities as well as by the return path discontinuities. Such of modeling at these data rates, we have to have accurate modeling of the serpentines. We have accurate modeling of the stitching vias and the proximity of them away from the signal layer transitions. The RAND simulations and concurrent optimization is a must for these data rates. In the next page here, we own that actually we can optimize only the impedance and the crosstalk independently. So the impedance and the crosstalk are not enough as appears in the pre-layout simulations. We need to optimize the accurate channel, including the return path, the signal layer transitions, the serpentining, the via stubs, the vias, the number of stitching vias, the property of the stitching vias from the signal layer transitions, and again, along with the transistor model simulations altogether. We can actually achieve that the 10-layer card, because of the state given to us, when read off between the impedance and the return path discontinuity, we can actually better performance by 6%, better than 12-layer card, because the return path discontinuity was an important parameter for this problem. It's not enough to have the post-layout optimized. We need also to optimize the driver performance in terms of slew rates, in terms of rise-fall mismatch, TCO mismatch, in terms of the emphasis, in terms of ODT and ODT linearity, which is on-die termination, in terms of the VI-edge, VI-low of the receivers, as well as the training between the stock-to-data relationship. Again, at these data rates, the answer is we need concurrent optimization of the whole channel. We can do that with such accurate modeling. And then moving here to the second example to Amolak to talk about the virtual EMI lab and the requirements for accurate modeling for EMI as well.
So now we are on to the second topic, which is looking at EMC and EMI simulations. And the first couple of slides I want to go through and just why is it important to care about this, and why is EMC EMI becoming so important? Well, the big thing to look at is this is the last bill to pass before shipping a product. And if a product fails EMC EMI specifications, there's some issues related to it. It results in embarrassing product delays. You can very easily fall behind the competition and also inadvertently introduce low-quality products, which could result in recalls or heating issues. So overall, all these add up to significant loss of dollars. So what is becoming important now? Didn't we hear so much about it 5 years ago, let's say? Because of three key trends. The increased density of commercial wire appliances like a laptop or a netbook or a soon-to-be Apple tablet, if you believe in the rumors. But anyway, there's a lot of going on. In addition to that, you have a lot of high-speed interfaces routed. So I've listed here all different high-speed interfaces running within that small proximity at very high data rates. On top of that, there's pressure to reduce cost, always. And so device manufacturers will try to minimize the layer count. They'll try to minimize the number of decoupling caps or other components. They'll try to minimize the cost of these connectors. So low cost means bad, typically, lesser quality designs. All of these add up to create more problems for EMI engineers. So for the current solution, how do typical EMI engineers tackle these problems? Well, no, it's usually a band-aid approach. And, because EMI engineers get so desperate and they really don't have the time or close to understand where the problems are coming from, usually by the end, they don't have any other option than just suppress it. So they try different band-aid options. Use different types of metallic shielding or different types of suppressor materials, but they're not optimal, and they're not guaranteed to work. And doing this at the very last moment costs a lot of money. So what if we can get to the source of the problem and actually do EMI design, just like signal integrity engineers do pre-layout simulations, do active layout EMI simulations, and also include post-layout, and generate good guidelines for EMI simulations. Now, this next slide shows a measurement, an EM scan measurement of a typical high-speed system, and it shows the different hotspots in the system. And the interesting thing to notice here is that the problem originated with the high-speed IC. And you can see that it is really a problem here. The IC is pretty quiet, but that's in fact the active portion of the circuit which is creating the initial noise that propagates through the rest of the channel. So as it propagates through the package and PCB, it starts to get worse. You can think of this noise is getting amplified as it's through the channel. By the time it reaches the world through the three structures, like the connectors or the cables, any dongles, becomes really, really bad, right? So what we learn from here is that if we can minimize the size of the EMI, which is coming from the IC, from the package and the board, if we can proactively reduce the EMI of these passive structures, we greatly improve our overall system EMI budget. And several examples to demonstrate this. Unfortunately, we cannot show all of them in a short webcast, but we'll show some of them. Now, because these need to be able to proactively predict EMI performance, Penny here at NVIDIA developed this concept of virtual EMI lab. So I'll pass back to Henny to discuss this.
all the time now we discuss the challenges to signal integrity, but EMI, as you can talk to anyone inside any company, they call it black magic. They would say that, oh, you guys are coming with a black magic type of solution space, because thing is actually done after the fact. Remember, 15, 20 years ago, signal integrity engineering was also a back-end type of a teamwork, that after the fact, we get the boards, and there is a problem, signal integrity engineers start engaging. It happens that right now, the same thing is running for EMI teams, that they only get impacted and intact with the design after the fact when we get the board and that doesn't pass the FCC requirements. Now, the problem at that time, everybody is on top of the head of the EMI engineer or the EC engineer, and no time left to find a solution space. And the EMI engineer has to come up with this black magic type of solution. Now, this idea of a virtual EMI lab is trying actually to put the EMI engineer ahead of the design before tip out of the silicon and before tip out of the board. Now, it's only possible for SIEs when we have accurate tools that can get us data within a reasonable amount of time. Then, using the top-notch software and hardware technology, like GPU acceleration, along with accurate full-wave techniques, you can get data within a reasonable amount of time. With our virtual Allegro board file, you can run the very well-known rules of thumb for EMI requirements and still go through a virtual EMI lab, which is running the full-wave techniques such as momentum, such as finite difference time domain for EM Pro, and do all the what-if analysis and try to understand the phenomena of the EMI radiations. Now, with the virtual EMI lab, it can feed back to modify the layout again before tip out. That can reduce a lot of the EMI problems. Not a big benefit to EMI engineers is that at this stage we can start developing an EMI suppression matrix, which is we now actually compromise and trade off between the different elements. As an example, we try to negotiate spec enabling versus improving the layout. Let's say spec enabling versus increasing the number of layers. If we requested such type of suppression factors, after tip out, it's going to be a big deal, and it's going to be a big hurdle and a big impact to both the gross margin of the product and a big delay to the launch. But we provided this suppression matrix ahead of time, then we are still in negotiation stage with designers of we can improve the layout by adding, let's say, 2 more layers, or we can still live with the same layout and improve, let's say, the chip TCO mismatch, or enable the spectrum on the chip, or let's say increase the number of decoupling on the package and on the die in order to reduce the amount of EMI radiation. At this point of time, the matrix of EMI suppressors, it's open for everybody. But after tip out, the elements of the EMI suppressors becomes limited because of the time to launch and because of the cost requirements as well. Now, virtual EMI lab can also help us during the debug stage, which is after tip out. So after tip out, we go to the 3-meter chamber or 5-meter chamber or 10-meter chamber to try to get the scan data. From this data, we can find out the problematic frequency points, and we find out the problematic interface. Doing a near-field EM scan, we can detect the hot spots, but it's enough to understand the radiation phenomena. Actually, no, we still need the simulation engine in order to give us a clue about the coupling phenomena, why this interface is radiating, what root cause of radiation. And we can also do all the what-if analysis on the virtual lab, on the virtual board. Remember that one of the hurdles and the difficulties for EMI engineers is that, say, when we take out the cap from the board and put back, we never go back to the same baseline of measurements. We all the time have something around 4 dB in the measurements in the chamber. But simulation, the good news is that take out the cap and put it back, you're going to go back all the time to the baseline dB limit of radiation. Therefore, this shows the importance of doing the simulations. Again, the key is to get the simulations within reasonable amount of time. I would like to say a special thanks really message to Chen Wang in my team, as well as to Davy, Dr. Davy from, as a professor of EMI in Belgium, actually using this technique in order to arrive with data within hours, within 10 hours or so of simulations, instead of data within weeks. The simulation used to take weeks, and instead of taking a week or so, now it's actually being down to a couple of hours. And then when we put hand in hand the software capability with the hardware GPU acceleration, you can get such type of reasonable data within the right amount of time. The output is actually a paper that is going to be presented by Chen actually in the Asia Pacific EMI conference in April. And this is work have been done by both Dr. Davy and Chen and Amolak and myself, which is really injecting the SSO, the simultaneous switching output noise, from our GPU on a real board, include all the complexity of the board. And the idea here is trying to understand where the onboard decoupling or onboard caps are effective in using the EMI radiation or not. We have a lot of tools in industry can look at the impact of onboard decoupling, on-package decoupling, on-chip, on-die decoupling to the impedance profile of the power delivery system. But did you ever look at the impact of the onboard decoupling to the radiation on a real board? So this is actually a real GPU card, and then we have an EMI radiation problem coming from the memory channel. And the idea is to inject the real SSO noise or simulated using accurate tools such as the Apache tool, and inject it into the GPU and try to find out whether the decoupling around the GPU is effective or not. The idea is inject the noise to the GPU card and optimize the decoupling to reduce EMI. And again, try to compromise and trade off between the decoupling on the board, decoupling on the package, decoupling on the die. Or at the end we have, let's say, to enable spec spectrum. But spec spectrum would only target the clock impact, and it may actually average the emission from this board. The next actually shows just one slide from Davy and Chen about the EMI radiation with caps on the top and caps, and you can see indeed there is a large separation of the EMI radiation by putting the critical caps around the GPU. Now on the bottom here you can see the same thing. This is the current density profile with critical caps and without the critical caps. You can see that areas are becoming reddish, they are hot on this plane, while they're becoming greenish, which is much quieter on this plane. You can see here of the 2D field radiations. The dotted lines are representing the case without caps, and the solid ones representing the great suppression of EMI by the critical caps around the GPU. Again, we got the simulations, according to Davy, I think within 12 hours or so. With the CPU alone, without this heterogeneous CPU environment, you get the simulation after a week or more than a week. With a week or after a week, I think that's pretty large time that the EMI engineer would not wait for this answer. But with hours, we can get this answer, and then you can try to find out which caps are more critical to the suppression of the field. I think it's becoming reasonable right now to provide EMI engineers with the tools that can debug and can actually provide negotiation of EMI suppressors when talking with the designers. Now, this you actually would leave it to Amolak, because this is the integration now. After we got the results, now we know that Maxwell's equations are 3D in nature, but we're looking at the fields in a 3D format. Now, if we ever looked at it in 3D, and that's Amolak.
Penny, and if any of you have seen the new movie that just came out called Avatar, and seen it in 3D, you'll right away understand what I'm talking about here. So what we've done is we've introduced this new technology in our Momentum and ePro tools, which allows you to look at your geometry as well as do processing, looking at the current density plots and far field radiation plots. You look at the results in true 3D, which I mean not just a 3D viewer we can see the kind of redirection, but also the depth. And again, it's a lot easier to explain and a lot easier to just see it in action. So in any video games, or if you have kids, have plenty of these 3D video games or any 3D movies, Disney movies, this new Avatar movie, you know exactly what I'm talking about. So very exciting, and it's actually allows you to visualize these very complex structures more intuitively, and it makes it really easy to visualize these complex phenomena. And I'll pass it back to Hani.
Okay, so the message from you guys is that the security and EMI engineers, they need actually to get a marriage between the top-notch and the cutting-edge software and hardware technology to get accurate data within reasonable amount of time. We did by looking at the accurate modeling of the passive interconnecting systems on PCBs, on the motherboards, on the packages. And we use the method of moments because the method of moment is a full wave technique. And it's very well suited for multi-layer structures because the method solution depends on discretizing the metals and discretizing the voids. You don't need to discretize the full 3D structure, especially that the substrates have no changes or no electric parameter changes within them. So the method of moments actually, it's a full wave technique that depends on the integral equation, discretization of the metals and the voids. It assumes actually electric currents on the metals, assumes magnetic currents on the voids, as well known by any moment method technique, and integral equation approach using the weighting functions for the currents and try to solve for these factors. The surface currents on the voids and on metals, now you can get the fields computation inside the structure, and you can also get the far fields. I agree with the SIE list that the most important thing at the end is, and the bottom line, is the correlation. And I agree with you guys that definitely we must the correlation either internal to the company or we actually can out-resource it outside, and that's the bottom line of the accuracy of the methods that we can use for the building of the passive interconnecting systems. So we use method to get the S parameters of the packages and on the boards. And it's not enough. We still need the fast transistor circuit simulations to get good modeling of the drivers and the receivers, because the linearity impact of the drivers and receivers becomes dominant into this multi-gigabit technology. So heterogeneous environment between the GPU and the CPU can give us fascinating speed up of the transistor model simulations. And simulations that can take 15 hours or a day or over a day can actually brought down to 3 hours and 5 hours. Now, looking at the fields, nature, they are 3D in nature, but we use all the time to look at them in 2D. Now, using the current technology that also NVIDIA actually headed in the industry about the 3D vision, you can actually take a look at the fields and the surface currents in 3D, so you can understand the depth and look at the fields in more natural way, exactly as Maxwell's and Faraday's proposed it for us long time ago. Finally, EMI engineers, they need the tools to prep the EMI suppression matrix ahead of time before tip out. They can in a much better situation stage to negotiate the suppression before tip out. There will be a miserable stage after tip out, and the number of suppressors are limited by the cost and by time to launch the product. But this virtual EMI lab idea, where you get full wave techniques such as the finite difference time domain, where difference time domain are really good for radiation problems because they actually can get a wide band simulation. And you can get complex 3D structures, such as the example we have shown here about the memory SSO radiation, and how the onboard caps can help in suppression of the noise, or of the noise on the card, as well as suppress EMI radiation. And take a look at the fields using 3D, the stereo vision. Again, you still need the heterogeneous CPU plus GPU to get fast simulations that you run within a week or after a week, and you can drop these simulations down to 10 hours or so, and you can get the simulations within a reasonable amount of time that can help the EMI engineer do all the what-if analysis, understand the root cause of radiation, maybe master the EMI problem instead of being called black magic guy. And I would say that for these complex approaches and techniques, it still needs experienced SI and EMC engineers that still must to really adopt this type of techniques that requires actually high level of expertise and to run the simulations in order to understand the data behind it. And that actually concludes our material. And sorry, just like, the last slide actually is from Amolak, so Amolak can go ahead, especially about the 3D vision.
Yeah, and the last slide is just concluding, and where you can find more information. We'll be at DesignCon, and we'll have a live demo of the 3D stereo vision and many other things. So if you want to come take a look, experience this new technology, stop by and be amazed. And we also have hands-on workshops coming up, which we'll be holding in Santa Clara in our Agilent office, and possibly at other locations in the future. And also there's a blog, then there's a link for, and also you can request an evaluation copy of ADS from this link. So that's the conclusion of our presentation. Thank you very much for attending, and we'll open the floor up for Q&A.
Great presentation, both Dr. Fehmi and Amolak. Colin, do you have questions?
Yeah, we've got a few questions. We'll try and get through these, and if we can't get through them all, we'll follow up with email. So the question, actually, this is probably for me. Fen and Arun both asking, is GPU acceleration for both the circuit simulator and electromagnetic solvers, including Momentum, EM Pro, and are these currently available? So all the things we talked about today are available. For the finite difference time domain and the circuit simulator, our transient convolution simulator, we have GPU acceleration. We have 3D visualization available today. It's a hot fix for ADS 2009 Update 1. And that's available in ADS for both finite, for both the FEM and Momentum. In addition, we have momentum acceleration, not through GPUs, but through server farms. That's called Momentum Turbo. So it's this thing. We haven't talked about Momentum Turbo today, but that's also available to accelerate momentum. But the visualization works for both Momentum and FEM in ADS, and it's available today. So for the technical team, that's enough product questions. The first is from Alan. Whether you want to know whether you're using linear drivers or transistor models. I mean, he notes that transistor models are usually not available in encrypted formats. Do you know the return loss of the transmitter and receiver, as they will modify the transfer function due to reflections, etc.? How do you get that with the linear models?
Yes, as we said, like in the material, that the linear driver model is just an approximation, and definitely we're encouraging actually at these high data rates to use the linear driver model. It's a matter of a fast simulations that should judge initially about health of the PCB and interconnecting system in order to differentiate if the problem really lies within the PCB or problem lies actually with the transistor or with the driver and receiver. Now, with the linear driver model, you still actually can depend on whether the return path is going to come from the ground or the power by connecting the linear driver terminals to the correct return path that is going to be connected to. So as an example, if the bus is an address bus and is switching relative to power, then you can connect your linear driver model between the signal to power. Or if it's majorly reference to ground, you can still actually connect it reference to ground. And I agree that the linear driver model is not going to be an accurate, but it's just like look at the health of the PCB. At the end, you must go to the transistor model simulations to include all these factors.
Great.
I hope I answered the question.
Good. I think that's it. So the next is from Bruce. He wants to know, how are the simulations validated?
They're actually through the memory shmoo and through the eye diagram measurements. So mainly, as an example, we have a current recent example of a DDR3 memory system on the motherboard. It's a mobile system with 2 SODIMMs per channel. And again, you do need to get the S parameters of the package, as well as of the board and the connector and the SODIMMs. And at the end, again, include the transistor model of both the drivers and receivers. And you can actually measure the eye diagrams in lab and try to find out, as an example, the worst bits. That actually we're able even to find out the worst bits within a byte plane, and we correlate actually that the eye drops for these worst bits. Now, to the question more directly, yes, we have to go to the lab, measure the eye diagrams even within the bits of a byte plane, and try out the characteristics of the eye, whether we see the same characteristics of the eye between the simulation and the measurements or not. Most of the time, again, if you do accurate modeling, then you're going to find correlation. If not, then we have to go back to the simulation model and find out what have been missed in the simulation model. Example, the transistor model PMOS process may be off. Then simple example that can happen. That you're using transistor model, but unfortunately the PMOS process files are not relating to the actual transistor behavior in the real silicon. So again, this all the time between going back and forth between lab and simulation is helpful either to correlate or to adjust the simulation model to get accurate correlation.
So then also from Bruce is how many unknowns, the computational domain size for the signal length runtimes you were talking about?
So like mentioned here, I think circuit 1, that's circuit 1 or circuit 2 or 1?
Yeah, I think the run times we were showing 1.5 hours and 2.5 hours. The matrix size for momentum. I think it's the question is asking about the momentum signal size, and I think the matrix size was around 20,000 unknowns.
I think if I remember well, I think it's between 2,000 to 30,000 elements. That's if I remember well.
Right. And also, if the question about the transistor level simulations, we're talking about roughly 20,000 to 30,000 transistors when we were showing the sim times. And actually, so that's the one with the 15-hour sim time, the normal sim time. And the other simulation that took 30 hours in HSpice, that one was about 55,000 transistors.
Good. Question also from Bruce. What set of DLC rules for EMC were used? And he comments, I sure hope it wasn't Cadence's EM control. I guess that's the E control because I guess he has some bad experience with that tool. Go ahead.
Actually, we use EMI stream from NEC in order to run the rule of thumb for EMI. And the nice thing about this tool, at least the reason for that we chose the NEC EMI stream, because actually dial in the EMI rules of thumb. Example, traces running close by to slots, traces crossing slots between planes, the sticking on the side of the board, the staggering of the planes instead of they all produce slot antennas. Again, all these rules, yes, I agree with you. Please refer to EMI stream for NEC. That's the one that we use here for rules of thumb of EMI. So
Bruce's last question is It's a humorous one. Do we get to see any 3D examples? Unfortunately, WebEx technology is limited to 2D currently. Hopefully, WebEx will upgrade their web technology and we'll be able to show you actual 3D examples. Now, you have to go and see the Avatar movie or come to DesignCon or to our workshop in Santa Clara office, February the 9th or the 11th. We're having two there, and you can see this thing live. Unfortunately, WebEx doesn't allow us to demo the 3D.
Not but
yet.
Clear that they will at some point support this. And just for your curiosity, there are 3D projectors now available that can actually project in 3D, and everybody can be sitting in a conference room with their cool 3D glasses on. So technology is coming in for real. You know, if you follow any news at CES, there's a lot of 3D televisions now coming out and 3D monitors that are coming out. So with this in the coming years, it's going to become mainstream. And actually, one thing I forgot to mention was, so this technology has been out and been used in games for the last 2-3 years. So it's not totally new, but we are the first EDA company to adopt this. And we showed this demo to a mechanical design team inside NVIDIA, and they were just amazed at the clarity of the structures they could see in 3D. And I assume that many companies, any CAD companies will follow and adopt this technology, but we happen to be the first ones to do this.
Yeah, I think meetings is going to be a lot more interesting if we get to wear 3D glasses and on a 3D projector you'll get better attendance meetings, I think.
I would add also really, Colin, please, that yes, indeed, what Amlak answers about the WebEx and so forth, the experts actually inside NVIDIA, they mentioned to us the same thing, which is a matter of transferring the 3D signal through WebEx. And really, the 3D, mainly technology depends on sending two pictures with a phase shift in between, and actually the active shutters on the glasses really sync up with these actually phase shifted images. As I understand really that they are working already on this technology, as Amalak mentioned, to try to transfer the 3D signal through the WebEx as well and through other meetings or net meeting type of internet meeting requirements. It is an ongoing, as Amalak mentioned, keep track of it. It's going very, very well.
Yeah, it's going to be very exciting. And I want to emphasize, this is not the old kind of red-blue glass that gave you a headache. This is really crisp and very comfortable 3D with using very high interlace shutters. Yeah. So, next question from Antonio. Is the simulation of the board with EM Pro related to the full board, or does it refer to a simplified one? Did you cut out critical nets for the EM Pro?
Actually, for the EM Pro, actually you got the memory channel included. So, depending on the type of simulations, here we're interested about the SSO. We kept actually all the planes of the memory channel, as well as you can still keep the traces. However, we didn't keep the traces for this specific example. We only kept the planes with all the details and all the stitching requirements on the board. So depending on whether the edition it comes from the SSO, from the part delivery, then you must include all the planes, or the simulations are really targeted, or the emission is coming from the data signals, then in that case you must include all the data signals. In most cases, actually, we have a couple of examples that you can still include all the signals, as actually in that first page of the material, we have included all the address signals because we have seen radiation in the lab coming from the address signals. In this case, you can include all the address signals, and you can still include a very large portion of the board, because say you actually need to simulate at merely at a wideband. This is actually page number 7. That you can see here the picture below. It does include actually all the address signals, and see that we still cut the board, but again, it's not expected that you can actually need to go far behind it, or at least you can check it out. You can increase the curve size and make it more rectangular and see that whether it does impact the antenna again or not. It's a very good question in the sense of you do need to try it yourself, whether this part is enough, or you need to go actually further away. On the SO example that we have shown here is that Davey have run. Yeah, this page actually number 23. As you see also here, like, it includes a cutter of it, but like, we think that that's pretty enough as well to get us a stable data. Because mainly that the wave travels and it has to die somewhere. And it needs to be at different trials to find that whether the simulation do stabilize and do saturate or not. Then you do need to include, if it doesn't, then you do include a larger cutter size. It needs a lot of investigation indeed to find the accurate settings of the simulations. That's why in the end of the material I've mentioned that yes, it does need actually experienced SIEMC engineers to run this type of complicated simulations.
Great, we've run out of time a little bit. We've got one more question. If we can go over a couple of minutes, we'll squeeze one more question. There's two more. One's a very quick one. One is about where the purchase the hardware for the GPU and the 3D glasses. I put a link into the chat window. You can see that. Click on that link. It goes to NVIDIA's website. Get the full information about the PCs, GPUs, 120 monitors and glasses. So the last question is going to be, if the number of caps increase, the leakage current will also increase. How to solve this? We'll do a couple of minutes and then we'll shut in. If you have any more questions, just email them to Emily at WebEx email and we'll deal with them offline. But this is the last question about the number of caps and the leakage current.
Yeah, I mean that actually in order to deal with the power delivery system, at least what we do here is that we use different tools like the IR drop analysis, first of all, to run the IR drop to understand that whether we do have actually enough number of stitching, whether we can deliver the correct actually requirements of the voltage specifications to the chips in order to meet the performance requirements. So that's from IR drop analysis. And a lot of tools in the industry can do that. The second portion is to meet the impedance profile. So again, you do need another tools to actually get the impedance profile requirements and to try to find out whether we met the impedance or not. These type of IR drop analysis and optimization of the decaps on the board, we most of the time actually we could put large number of caps on the board because of the cost as well as because of the real estate. Again, you can refer to the IR drop analysis for DC type of drops as the impedance profile simulations and measurements in order to find an answer of whether the number of caps is good or bad, and whether we met the impedance profile requirements or not, we met the peak-to-peak noise or not, we met the jitter specs requirements or not. It's not only enough to look at the peak-to-peak SSO noise at the different voltage probes and voltage pins. We need also to look at actually the jitter impact of different chips, how actually this peak-to-peak SSO noise is actually transferred to the jitter that impacts the signals. Now, the second question that we added in this material here, which is page 23, it's about how actually those caps impact the emission when there is an injected SSO noise. So those three portions are drop analysis, the impedance profile, simulation and measurements, the third portion of the emission damping using these on-board and on-package and on-die caps, all need to be available tools for SIE and EMC engineer to get an answer to your questions.
That's it. Emily, to wrap up.
Great. Thank you. Thank you, Colin. Thank you, Dr. Femi. Thank you, Amalak. What a great presentation. And thank you to everyone for your attendance, your great questions, your participation. Again, if you have any questions, please feel free just to reply to that WebEx email, and we will be sure to forward on to either Dr. Femi or Amalak. Thanks again. We have a great remainder of the day.